All right, let's jump right into this explainer. Today we're tackling something totally mind-bending. We're going to examine the exact equations that let us translate abstract topology directly into the physical structure of spacetime itself. We're unpacking a framework known as the Adelic assembly architecture, and I promise you, it's going to completely change how you visualize the physical world around us. Here's our mathematical roadmap for today. We'll start with the Adelic assembly pipeline, move into the core assembly identity, explore the cross-channel convolution engine, break down arithmetic stress and curvature, and finish up with the topological assembly code. So, Part 1, the Adelic assembly pipeline, translating topology to physics. To really grasp this, we have to start with the Farrell-Jones Conjecture. This is an absolutely monumental concept in geometric topology. Proving this conjecture gives us what mathematicians call topological rigidity. In physical terms, it means the universe is capable of building its massive, continuous macrostructures purely from digital, one-dimensional cyclic subblocks. We are literally talking about assembling the universe from the mathematical equivalent of simple lines and circles. Think of this entire pipeline not as static gluing, but as an active process. We're moving from assembly maps in pure topology, passing those maps through Adelic data decompression, which acts as our arithmetic engine, and outputting emergent 4D Ricci curvature. It is an active, physical data decompression of the universe's geometry. Now, it's really crucial to see how the Adelic Langlands approach completely bypasses the failures of classical homology. In classical methods, mathematicians hit a wall of combinatorial complexity, basically nonlinear winding anomalies called Whitehead torsion that just made assembly maps fail. But the Adelic Langlands method, it maps the system onto the spectrum of a generalized Dirac operator. This means global automorphic rigidity steps in and forces strict unitary closure, completely regularizing those errors away. Which brings us to Part 2, the core assembly identity, where we look at decompressing the group ring. Looking at this equation, we see the universal assembly map operator. Notice the left side. These are your local, virtually cyclic microcomponents. The operator is taking on the massive task of grabbing these simple, unramified data packets and gluing them together to generate the incredibly complex topological space of a global group ring, which you see on the right. To avoid those messy, nonlinear, winding paths we mentioned earlier, this equation splits the global trace into its continuous Archimedean component and its discrete non-Archimedean components. It's a precise factorization over the adele ring, and it's driven entirely by stable, unramified wave harmonics that perfectly represent our cyclic subgroups. Next up is the integration filter, which essentially operates as a data transmission engine across the adele ring. It grabs those pure, unramified local wave factors and meticulously filters them into a global L function. But for this global group ring to stay structurally stable and unitarily closed, we have to enforce a critical requirement of mathematical reflection symmetry. And here is how that happens. The clamping mechanism on the right of this equation is everything. Global J-theory stability forces the mathematical conductor, the n value, to exactly equal 1. When n equals 1, the local conductor exponent must be 0 across all primes. If you check the inequality on the left, you'll see this absolutely mathematically crushes the informational divergence between the kernel and the co-kernel. The unapproximable Whitehead torsion gets zeroed out entirely, forcing the assembly map to be a perfect isomorphism. But what happens when things get tangled up? Let's look at Part 3, the cross-channel convolution engine, processing group ring intersections. When two independent group ring assemblies intersect, we process the interaction using a multi-step Rankin-Selberg convolution. First, we set up two independent automorphic representations for the intersecting groups. Then, we identify their local Satake parameters to track their internal eigenvalues. Finally, we intertwine them to mathematically measure the exact phase mismatch between the two. Zooming in on the local micromath here, the inverse determinant of this equation computes the mutual intersection of the characteristic polynomials over the discrete unit disk. It's structured as a degree n squared polynomial. That means it is painstakingly tracking every single cross-channel cyclic eigenvalue combination. It's basically calculating the cross-entropy generated the moment these fields interact. Now, zooming back out to the global level, this equation limits the mutual geometric volume of those two intersecting group rings. Check out that logarithmic derivative on the right side as s approaches 1. If those topological distortions try to decouple from their cyclic baseline, that derivative would just diverge straight to infinity. But the global functional equation steps in. It physically squeezes the K-theory volume, stopping unbounded dimensional inflation or the infinite generation of vacuum entropy right in its tracks. And if that assembly bound is squeezed to its absolute breaking point, we reach part 4, arithmetic stress and curvature and the creation of mass. Focus on the bottom equation for the 4D Ricci curvature tensor. When overlapping non-commuting phases completely saturate the assembly bound we just talked about, their energy overflows into the local primes. This creates an arithmetic stress factor. And this stress acts directly as a macroscopic stress energy tensor. It forces continuous 4D spacetime to curve instantly, rerouting the information to stabilize itself. Let that sink in for a second. Gravitational curvature is literally the physical expression of a saturated manifold assembly bound. Which perfectly sets up our final section, part 5, the topological assembly code, a fault-tolerant universe. We can literally map these equations onto a quantum information framework and construct a quantum error-correcting lattice. By assigning physical data qubits to the equivariant cells of our cyclic subgroups, the boundary operators become generalized parity checks. This means virtually cyclic classifying chains act as the actual physical substrate for fault-tolerant logical qubits in the universe. And here's the mechanism in action. Think of the Satake assembly operator as a multi-qubit measurement circuit. In a flawless, unramified baseline, evaluating this operator yields exactly 1. But if a winding anomaly tries to tear spacetime apart, it creates a local ramification event. This spikes the local conductor index, and our mathematical circuit immediately reads it as a non-zero error syndrome, exactly like a quantum computer detecting a phase slip error. Because the global functional equation rigidly clamps the overall cosmic conductor to exactly 1, the universe simply cannot tolerate these errors. Looking at this explicit operator equation, any local nonlinear Whitehead torsion anomalies that pop up are forcefully crushed by this tensor product. This instantly repairs the spacetime fabric and secures an invariant codistance. This absolute interlocking network unites our entire journey today. Topology provides the goal, fault-tolerantly assembling complex spaces. Prime number arithmetic provides the engine, the Adelic Langlands Program strictly regulating cross-entropy. And smooth, stable physical laws, the macroscopic universe we actually experience, are just the final cosmic runtime display of this incredible arithmetic web. This reveals a profound physical paradigm. The large-scale universe doesn't tear under extreme stress. And it's not holding together by chance. It holds together because it is actively running a homological assembly error-correcting code. Manifold rigidity literally is quantum error correction. So I want to leave you with this final provocative thought as we wrap up this explainer. If gravity and mass are just the overflow of an arithmetic boundary, and the continuous dimensions of our universe are simply a decompressed mathematical shadow of cyclic subblocks, what other digital codes are hiding, computing away in the quantum vacuum right now? Take some time to process these equations and keep questioning the very fabric of our reality.